Greetings to Mr. Hajik and everyone. Thank you for giving us the chance to record this remedial demo presentation. We are from the Faffi group with our final project is called Planetarium, and our group consists of Andika, Malvin, which is me, Hanif Furqan, and Rafli. We are explaining what is planetarium first. This is a 3D digital planetarium experience simulating what it feels like to fly an astrojet around our solar system. And you can travel up close to the planets and expect them to display information about each one. And the features primarily will be shaders and geometry, and then lighting, animation, and user interface. Today I will explain the shaders part and the lighting part and the geometry part. I mainly will be explaining about the planets for the geometry because the geometry consists of the planet and the astrojet or the plane, but I will be covering the planet part. Okay, so first I would like to show what our final project looks like. We are using Unity. This is the main menu and you can play it. Then you will be flying a plane like what I explained before. The A and D will be rotating the plane, and to move forward you can press space. To turn left and turn right you can use Q and E. And these pink trails around the sun is the orbit of the planets rotating and revolving around the sun. And the next features will be the UI where you can approach a planet. Let's say this is the Earth. When you're approaching the Earth, you will be transported to another scene that shows information about the Earth. Alright, next I would like to explain how the planets. I think I will go with the sun first. How the sun is made. Okay, so this is what our sun looks like. As you can see, it is just a sphere with a shader. And this is what the shader looks like. We are using the shader graph from Unity. Okay, the Unity shader graph here creates the sun with solar flare effect. And the key component is the radial shear. The radial shear here, which is used to add a radial distortion to the UV coordinates, simulating the flare appearance of the sun. And it takes input of UV0, which is the base UV coordinates. And then the center strength and offset control how strong and where the shear effect distorts the UVs. And the output is moved to the Voronoi noise. And the Voronoi noise here is used to generate a cellular noise pattern to mimic solar surface activity. And the power node is used to adjust the contrast of the Voronoi noise, and the effect is to make the dark regions darker and the bright regions brighter. And for coloring the flares, the power node here output is multiplied by a custom cell color here to add an orange red tint, giving it the solar look, how the sun is look like. And next is the base layer and additive blending. The solar flare layer is added to another base color layer called the base color here using an add node. And the effect of this is blends the bright flare regions on top of the softer base glow to enhance the sun's appearance. Oh yeah, and this part here, this is actually the important part is the time and the cell speed, which is multiplied to result in a moving Voronoi noise here. And going back to the add here, and the result of the output is uh, moved to the fragment output in the emission part. This is used to create a glow effect on the sun, where the bright areas emit light, enhancing the glow effect of the sun. And and yeah, this is what we get for the sun. As you can see, as you can see, the sun is showing a little explosion around it, which is the solar flare. This can be achieved by using the shader graph I have explained before. And next for the planets we are using a procedural generated code, so we do not do any texturing manually. And I would like to thanks shout out to this channel from Sebastian Lake, which helped us a lot on creating the procedural planet generation. And we use the tutorial there to create the planet here. For example, I would like to take the Earth here. As you can see, this is the Earth. It is not 100% accurate like what our Earth looks like because this is procedurally generated and it is kind of hard to tweak the parameter to mimic how our Earth is actually look like. So I will explain the code a bit for the procedural generation part. There are a lot of codes. I will not explain all of them in detail. So the first one is this terrain phase code. This terrain phase is used to construct the mesh. So here we are not creating a sphere game object from Unity. We are creating it from the code. That is why there are mesh children here from the Earth Inspect game object. This mesh is actually generated from the terrain phase code here. And next is the planet.c# here. This is serves as the controller for generating the entire planet. And this also organizes the terrain phase before for the cube faces and determines whether they should render based on a face render max or not. And this include an update methods for reacting the change in shape or color settings. Well, this part is actually controlling how the planet will be generated mostly. And the next is the color generator here. This is generates and manage the coloring of the planet and updates the planet's material to reflect elevation data and biome transitions. Next is the color settings. This is a scriptable object. This is used to define the color settings for the planet, like the biome gradient and how the ocean will look like, and control the blending details too. Next, for the min-max. This min-max is a utility class to track the minimum and maximum values and used to store elevation, extremes, or other ranges during the planet generation process. This will actually uh, take a lot of part on the shader that I will be explained later. And next is the noise. This is taken from libnoise.net, so we just take it from an existing code where you can see it here. This part is basically implements a simplex noise algorithm that is suitable for mostly procedural generation. And next is the noise filter factory. Is a factory class that produces noise filters based on the configuration provided in noise settings. The noise settings is here. It is also a configuration class for different noise settings that includes all the parameters you can tweak later in the Unity inspector. And this is the rigid noise filter. This rigid noise filter is used to implement a rigid noise filter that is used to create a jagged terrain, create a sharp terrain for the planet so that you can emphasize higher peaks like the mountain. And then the shape generator. I will go into the simple noise filter first. This simple noise filter is used to implement a sim simple noise filter that is useful for less dramatic terrain like the hills or the plains. Meanwhile, for the rigid noise filter here is used to create the mountains. And next is the shape generator. This is used to generate the planet shape based on the shape settings and a series of noise filter. And the shape setting itself is actually here. It is a scriptable object that is used to store configuration for the planet shape and noise layers. So that's basically what I can explain. For the details, you can actually watch this series. It's a good series and it helps a lot. And next, for the shader of the planet, this is the shader graph of the planet. And it consists of a lot of nodes. And the first one is the input UI coordinates here. It is put set to UV0 and it is split to extract the X and Y components of the UV coordinates. Next is the elevation control. This part is a elevation min max, which is specified somewhere in the code, I believe. And this is where the this part, the elevation min max. I said before, the elevation min max here is used to control the color. So that is why we put it in the shader where the higher peaks will have different color and the lower peaks will have different color. And then the split part here is splitting the components like this one. And then the inverse slope here is used to scale the UV coordinates into a normalized 0 to 1 range based on the elevation values. And then next for the lerp, these two inverse lerp here is taking the normalized UV values as input. This determines the height and elevation mapping for the X and Y values. And then the floor node here, the output of the inverse lerp, is moved to the floor node here, which quantize the values to create sharp steps like clips and other elevation bands. And the one minus here is inverts the quantized values for smoother blending or transitions between bands. And the lerp nodes is used to interpolate between values from 0 to 0.5. And the other one is 0.5 to 1. And the multiply nodes here is used to multiply the output of the lerp nodes to combine effects and smooth out the result. And finally, we can add the color texture. The a planet texture here, planet texture T2 is sampled using the final process UV. The sampler itself is using the linear filter and the clamp wrapping to ensure smooth transitions. And the base color assignment is the output of the sample texture 2D is pushed to the fragment here to on the base color. Also, we are using a smoothness property. This part is to control the smoothness of the planet surface. This is connected via a multiply node for further adjustment. And that's it. So basically the shader graph is generating elevation-based banding like mountain valleys or terrain stripes, and samples of planet texture to overlay detailed color variations and provide smooth transitions between elevations using lerp and blending nodes. And next I will be demonstrating a bit for creating the planet. So this is I've created a mesh. From the code, you can just create an empty game object and attach the planet script here. And then you can tweak a lot of these parameters to ensure you like how your planet looks. So I will be explaining the parameters, some of the parameters. And the first one is the resolution here. This basically controls how many triangles this game object have. And the face render here is what do you want to render. You can render the top, the bottom, the left, and this generate planet is used to generate the planet. After you tweak all of the parameters, you can use generate planet, and the planet itself is actually changed from before is a white colored sphere, and this is how it looks like because before I have already tweaked a little bit of these parameters, and this is what we get to the important part of the parameter is first is the strength here. This determines the overall intensity of the noise layer, and the higher values makes the terrain more exaggerated and elevated. And next is the number of layers is basically the layers, the number of noise iterations. More layers add detail but increase the computation. And the base roughness is used to control the initial frequency, like how tight or how spread out the noise patterns are. And next is the roughness is used to multiply the frequency after each layer. Higher values make subsequent layers increasingly rough and detailed. And next is the persistent here is used to control how the amplitude or intensity change across layer. Next is the center is used to offset the noise pattern in 3D space. Changing these values can shift the terrain features. And next is the mean value is used to affect the elevation baseline, effectively clipping lower noise values. Reducing this mean value is used to uh, makes the valleys on the planet deeper while increase the overall terrain. That is for the simple noise. And the rigid noise, what makes it different is the weight here. The weight multiplier. The weight multiplier itself is used to control the impact of sharp peaks. Higher values exaggerate the peaks and suppressing the valleys more, giving the planet a mountainous look. And this is the color test is used to where you can assign the material that you have created from your shader graph before. Like this one, you can right click and create a material from it and assign it to the color test here. And the biomes is used to make the biomes. You can play with this around to create like you want your planet divided into three biomes, for example, like the bottom one is savanna, or and the middle one is mountainous, and the upper one is full of snow, you can do that. You can just create more biomes here and it will adjust automatically. And this is noise to control the distribution of the biomes color, so and it's not distributed evenly. And next is the ocean color. This is basically the base of the base, the ocean. The blue things here is actually coming from the ocean color. Yes, you can play around with this, and I think that's all for my part. Thank you very much.
Alright, so in this section, I will explain about orbital path in our solar system. So firstly, we need to define the constant of G, right here. And then we need to start this class from the void start. So in this void start, we need to find object with tag celestial, and we need to next we need to call initial velocity class function. I mean, so in this initial velocity, we need to use the gravity. Yeah, we need to use the gravity. So in this gravity, we just implement the universal gravitational law by Newton. So right here is G times m1 times m2 over by r square. So this is the formula we just implement in this one. So after that, we use it to this initial velocity. So every planets will be have the gravity, all right. But and every planet when it's have the revolution to the sun, it will have centripetal force. So we know that the second of the Newton law, that is F equal to m times a. A is for acceleration, and a is equal to v square over by r. And this two equation is the same uh, units. So that is all using Newton units. So we can just compare it, and voila, we have this velocity for our project. So this initial velocity, so right here, is from this equation, right? So that is for our orbital path. Next, I will explain about the planet rotation. So in this planet rotation, we just use this transform rotate. That is vector 3 down rotation times rotation speed times the delta time. And in this space object, and we in this rotation, as we know, mostly of the planet is using the y axis for the rotation. So we just using for factor 3 to down. It just uh, so the rotation it will be like in Indonesia we use kaidah tangan kanan, yeah, right there. And so factor down is just this factor is down and we have to rotate it in Indonesia searah jarum jam. So like that. So that is our formula for planet rotation. Okay, that is all I can explain about this section.
First of all, yeah, first of all, let us to declare six variable, which is pitch power, roll power, yaw power. This is just for pitch up and down. Roll is like diagonal of the spaceship. So if your spaceship is not just static, you can diagonal it like 60 degree or maybe 880 degrees. So the spaceship will be upside down. And there are also yaw power. This is just for left and right. And there is for acceleration speed and deceleration speed. And we also declare our max engine power, so it don't go off-road. So there's also current engine power, which is applied to our current spaceship. And there are also some active roll, active fit, and active PO. We will gonna use it later. So there is only two function, which is void update. This is will gonna be update was update perfect. So first of all, let's go to here. It's just to like control the acceleration speed or deceleration speed. So the acceleration speed is going up if you press the space, and if you don't press anything, you will get a deceleration speed until 0. We are gonna use MATLAB, which is just maximum and minimum power based on acceleration times time delta time. So after that, if you use forward movement, we will gonna transform your position based of this equation. So we're gonna move forward, and after that, we gonna get our input. You get the vertical, horizontal, and the yaw input is based on here. So it just your input is basically just so your spaceship can go left and right. And after that, we are gonna apply rotation in this transform rotate. So this is like just rotate your spaceship so it can go up and down, left and right, and active roll is just rotated. And the funny thing is, if your active roll is doing 80, so your position of the ship is upside down, the all control will be reversed. So actually, we need to get a maximum value for maximum and minimum value for active roll, but we are not do that because it's a little bit funny when your control jumbled up. So next, let me explain about the spaceship radius handler. So the use of spaceship is just to the user can collide to some planet, and we the from that the planet will show up about the information about the planet. So that in here we just like if the spaceship enter the collider of a planet, the the we will get a game object name, which is the planet name, and there is also display message. It's just simple display message. And after that, if it is in collider, we will set it in true, and we are gonna go to scanner load routine. So in this scanner load routine, then we just compare what is the name of the planet, and based on that, we are gonna load a scan that based on the maybe you interrupt the collide to the sun. We will show you information about the sun, and after you exit, you will gonna go back in your initial position. It is the first time when you play a game. Yes, so it's actually simple. For me, that's all. Thank you.
Okay, everyone, I will demonstrate my part. This is the UI for Planetarium. It's just 3 scenes for the UI. The first one is the main menu, and the second one pause, and the third one is the inspect the object. Our object is the galaxy itself. So in the Planetarium, the main menu just simple button. The pause is 2, and the third one is planet name. I mean the galaxy object name and the detail, and there's the back button too. Yeah, just like that. Okay, so let's go to the code, and this is the event code where they execute the planet, how they load, and just like that. I'm sure my friend already explained this, I just review it again. So okay, this is the spaceship handler code where we handle how the spaceship and how the space radius is handling. So when the spaceship is close enough, they will load the inspect galaxy object, and this is the spaceship controller script where we define how the spaceship go, and I'm sure my friend already explained about this as well. It's the accelerate and decelerate and the engine power. We don't have we just go forward and go back. To go back we need to go U rotation with our spaceship, and we put the anchor in the wings, so when we rotate our plane upside down, our right turn become left turn. Maybe I will show you in a bit. Okay, so the anchor is in the wing and the right turn is like that, left turn too. So if we rotate the axis upside down, the right turn is gonna become left turn. So just like that, it's supposed to be right turn and it's become left turn, and that's it. Let's go back to the code. This is the scene manager. It's just the bridge for the project and load the solar system screen, just like that. Okay, so let's go to the main menu system. It's just a simple system. It's just a button system to go to the other scene and for quitting the program. Other than that, there's nothing here. And the pause system is where you press the pause, it will subtract 1 point from the time scale, and the time scale becomes 0, so it will render everything to freeze. And when we unpause or resume the game, the time scale become 1 again, so everything backs to normal. Okay, maybe that's it. Thank you for tuning in, and maybe you can subscribe to our channel and see other videos. Thank you for tuning in. Bye bye.